And remember, don't try anything you're about to see us do at home.
Ever. We're what you call experts.
Today on ThrusterBusters, we investigate a space propulsion concept that uses microwaves and magnets. Who are the ThrusterBusters? Ari Eckhaus and Ari Eckhaus. Between them, nearly 3 years of PhD experience. They don't just build the thrusters, they put them to the test. Electric rockets are becoming widely used due to their high fuel efficiency, which allows for increased payload mass. However, in order to operate, many of these electric propulsion systems require high power, which is often generated using large solar panels. Unfortunately, for small satellites, power is at a premium. This means they cannot use conventional electric propulsion systems and instead require novel, low-power thrusters. One promising candidate is the ECR magnetic nozzle thruster. Alright, so ECR magnetic nozzle thruster, what the heck does that mean?
So ECR stands for electron cyclotron resonance, which sounds scary, but really it's not that bad. Resonance is actually something that we encounter on a regular basis. For example, on a swing set, you can kick your legs in resonance with the swing to gain energy and swing higher. This thruster uses the same concept to couple energy into the electrons of a plasma. The injected electric field oscillates at some frequency, which is in resonance with the electron motion about the magnetic field lines, and in doing so, it couples energy into the electrons and heats them up.
Okay, so the resonance explains how the electrons heat up, but how does the thruster generate thrust?
Well, that's the job of the magnetic field. Once the electrons are hot, as you can see here, they stream away from the thruster, leaving behind the heavy ions that are very massive and cold. And this charge separation creates an electric field, so the ions want to follow the electrons downstream, which generates thrust on the device.
I see. So why again is that a good thing for small satellites?
Well, there are several reasons that this is desirable for small satellites. First, these thrusters can operate at low power, less than 100 watts, because the electron cyclotron resonance is very good at heating up the electrons. Secondly, these devices don't require an electron source to ignite or neutralize their beam, which is unusual compared to other electric propulsion systems. And then finally, because they don't need an electron source, they can run on a variety of propellants that would otherwise be hazardous to these electron sources. So ECR thrusters can run on things like air and water.
Nice. So does that mean they can glow pretty colors?
I suppose it does.
Alright, perfect. So where do we test one?
I think I know a place.
We've come to the University of Michigan's Plasma Dynamics and Electric Propulsion Laboratory, where they have one of the biggest vacuum chambers in the world. Inside of here, they test all sorts of electric propulsion systems, ranging from Hall thrusters to the ECR magnetic nozzle thrusters that we'll see today. My name is Ari Eckhaus, and I'm a third-year PhD student here at the University of Michigan Plasma Dynamics and Electric Propulsion Laboratory, and my research focuses on characterization and optimization of ECR thrusters. So here I have our device. It's been optimized to operate at about 30 watts on xenon propellant, and you can see we have a central antenna, which is where we inject the microwaves into the plasma, and the magnetic nozzle is created using a set of permanent magnets at the back of the thruster. And then behind me is our vacuum test facility. This is Junior. It can achieve about 1/1 billionth of atmospheric pressure to allow us to simulate a space environment. Inside of the chamber, we also have a series of diagnostic tools like a thrust stand and several plasma diagnostics, which allow us to investigate how many ions are being produced, as well as how fast those ions are going. So with those tools, we can better understand how the ECR thruster is performing. Now the only thing left to do is to pump down and get started. After pumping down overnight, the vacuum chamber is ready for testing. Ready to test ECR thruster in 3, 2, 1. When we go to actually test the thruster, we light it using a big puff of gas, which allows us to initiate the ECR reaction and ignite a plasma discharge. Once the thruster is stabilized, we let it run for about an hour so that all components can reach thermal steady state. Once that's done, we start collecting our probe data and finally take a thrust measure.
Alright, the results are in. At 30 watts, the thruster produced a whopping 750 micronewtons of thrust. This is approximately equivalent to the weight of a single grain of salt. Now, this may not sound like a lot, but keep in mind that the premise of electric propulsion is to provide a small amount of thrust for a very long period of time to move a spacecraft from one point to another, but use fuel in a very efficient way. What about the efficiency? Total efficiency of the device was about 10%, meaning that only 1/10 of the power put into the system was recovered as power in the plasma jet.
Well, that's not very good. Why is it so low?
Well, the probes showed two primary reasons that performance was so low. First, the thruster just was not producing very much plasma. Of the neutral propellant that was injected into the thruster, only about half of that was actually ionized and converted into plasma. This is low compared to other state-of-the-art thrusters. The second issue was that the ions that were produced were not being accelerated to very high speeds for the amount of power that we were putting into the system.
But if we could solve these two problems, that means ECR thrusters would be a very good option for small satellite propulsion, right? I, Even though performance is not very good right now, I think I'm still going to call this one plausible.
I agree. I think it's plausible that ECR thrusters could be a viable option for small satellites in the future.